Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
We're surrounded by these incredible machines every single day. But have you ever really stopped to wonder what's actually going on deep inside? Well, today, that's exactly what we're going to do. We're taking a journey through scale, starting with the big picture and then peeling back the layers to see how these modern marvels of engineering truly work.
Okay, so think about it. We see them everywhere, right? Car factories, giant warehouses, these powerful, super precise industrial robots. But what are they really when you get down to it?
So we're going to start at the macro scale, the big stuff. This is where machines perform these massive tasks with just incredible strength and speed. And what you're looking at right here, that's your typical floor-standing industrial robot. It's this amazing blend of raw mechanics and super smart computer control. And it has absolutely transformed manufacturing as we know it. Okay, so a robot's capability, it's often defined by something called its degrees of freedom. It sounds complicated, but it's not. It's basically just the number of different ways it can move. So for a robot wrist, like the one you see here, those are typically pitch, roll, and yaw. Just those three simple motions, but when you combine them, whoa. It lets the robot point a tool in pretty much any direction you can imagine.
But here's what's really interesting. All of that incredibly complex movement, it actually comes from surprisingly simple building blocks. And this is where we're going to make our first jump in scale. We're moving from the whole robot down to its inner workings, what I like to call the very bones of its motion.
All right, let's zoom into what's called the mesoscale, right into the bones and joints of these machines. These are the mechanisms that actually create all that motion. Now look on the right. You see that? It's a simple 4-bar linkage, just 4 rigid bars and some pivots. Looks almost childishly simple, right? Well, now look at the left. That exact same principle is being used in this upside-down flipper to flip things over on an assembly line. Isn't that cool? It's just a beautiful example of how really clever geometry is the secret sauce behind complex motion. These mechanical principles, they can be used for way more than just moving things around. So here's a thought for you. What if a machine could do math? I mean, actually perform calculations without a single microchip? Does that sound possible?
Oh yeah, absolutely. And this is a brilliant illustration of how it works. What you're seeing is an analog computing mechanism. It uses a super simple geometric principle, similar triangles, to multiply 2 numbers. You just adjust the input racks to represent your X and Y values, and boom, the output rack physically moves to the exact position that represents their product Z. It's literally math made mechanical. It's just pure genius, right?
So you see, whether we're talking about a simple flipper or a mind-bending mechanical calculator, all these intricate parts have to start somewhere. And they all start in the same place, the digital world. They don't just spring into existence, right? They have to be designed.
Yeah, before a single piece of metal ever gets cut, every single component is born as a digital blueprint in what's called a computer-aided design system, or CAD. But here's a fascinating little insight for you. The D in CAD, it stands for design, but you could argue it's still essentially computer-aided drawing. Why? Because all the creativity, all the ingenuity, that still has to come from the human designer.
And man, CAD has evolved like crazy over the years. I mean, we started with simple 2D drafting. Think of it like a digital piece of paper. Then we moved to 3D wireframes, then surfaces. But now we use something called feature-based parametric modeling. And what that means is the models aren't just dumb shapes anymore, they're intelligent. You can change one dimension, and the whole model automatically updates everything connected to it. It's a total game changer. It's this level of sophistication that lets designers create these incredibly complex parts, like this indexing wheel you see here, with just absolute pinpoint precision. And here's the really cool part. They can calculate physical properties like mass and volume right from the digital model, so you can check if your design is going to work before you ever spend a dime on cutting metal. And it's not just for single parts, not at all. This process can handle entire, super complex assemblies, like the suspension for a bobsled you're looking at right now. Every nut, every bolt, every single component is fully realized and tested to see how it fits and functions, all inside the computer. You can imagine the immense amount of time and money that saves. Okay, so we've got the perfect digital blueprint. The big question is, how do we turn that into a real physical object that you can actually hold in your hand?
Well, this is where the magic really happens. It's a process called rapid prototyping, but you probably know it by a different name, 3D printing. The process itself is just elegantly simple. You make your design in CAD, then some smart software slices that model into thousands of super thin horizontal layers. You send that file to the printer, and the machine just builds it, one tiny layer at a time, from the bottom up.
And there are so many ingenious ways to actually build up those layers. For instance, stereolithography uses a UV laser to harden a vat of liquid resin. Then you've got selective laser sintering, which uses a powerful laser to fuse together fine powders of plastic, or even metal. You can even use paper, I'm not kidding, in a process called laminated object manufacturing. And of course, there's the one most of us are familiar with, fused deposition modeling, where that little nozzle extrudes molten plastic line by line. Okay, let's take a breath here. We've gone from a giant robot arm all the way down to its mechanical guts, then to its digital DNA in CAD, and finally to its physical birth through 3D printing. So now it's time for our final, and I think most dramatic jump in scale.
What happens when you take all of these principles, the design, the manufacturing, and you shrink them down, way, way down, to an almost invisible scale? Well, we enter the world of 1 micrometer. That's 1/1,000,000th of a meter. Welcome to the world of micro-electromechanical systems, or MEMS for short. And let's be super clear here, these aren't just tiny static models. Oh no, these are fully functional machines with moving parts, all fabricated on silicon wafers, just like computer chips. I mean, just look at this comparison. On the left, a normal electric motor. And on the right, a fully operational micromotor built with MEMS technology that is smaller than the head of a pin. It's just unbelievable. Engineers use techniques they borrowed straight from the computer chip industry to create these complex moving parts out of a material called polysilicon. And get this, at this tiny, tiny scale, polysilicon is actually stronger than steel. How wild is that? And these little machines, they're already all around us. They're in the sensors that deploy your car's airbag, and they're the accelerometers in your phone that know when you turn it sideways. The results, honestly, are just mind-boggling. Take a look at this. This is a fully operational steam engine that is smaller than a single grain of salt, and it works just like a big one. An electric current heats up a tiny drop of water, the steam expands, and it pushes the pistons. This one little device perfectly wraps up our whole journey, doesn't it? It shows the exact same fundamental principles at work, just on a completely different, almost unimaginable scale. So from giant factory floor robots all the way down to invisible engines, the same core principles of mechanical design, movement, structure, material, they all still apply. It's just the scale that changes. Which leaves us with one final and I think really exciting question to think about. If we can already build engines smaller than a grain of salt, what in the world are we going to design next?